Hello, it's GCSE Physics Explained. I'm going to go over an Edexcel paper, paper 2. It's foundation, but there'll be a lot of overlap between the foundation and the higher papers, and I'm going to use this as an opportunity to explain the physics, not just tell you what the answers are and then you don't understand them. What I recommend is that every time that I read a question out, before I show you what the answer is, pause the video and if you try it yourself before I reveal the answer, alright? Right, here we go then. So this paper is Physics Additional Science or Combined Science, Unit 2, Physics for Your Future, Foundation Level. And this was from June 2017. That shows you a list of the formulae that they provided. So each different paper, they give you a different formula, but it's best to try to memorise the formula anyway. I've got a video for all the different formula on my channel. Right, question 1, motion and forces. The diagram shows a cyclist during a race. Many quantities can be measured during the race. Which of these quantities is a vector quantity? Put a cross in the box next to your answer. A vector quantity has got both size and direction. So if we look for velocity, yeah, when you're quoting for velocity, you say it's like 8 meters per second, and you'll say north, east, south, west, or to the left or to the right. So velocity is a vector. Mass, no, that's just a size, like kilograms, 8 kilograms. Distance is just a scalar. A scalar quantity has size only. Question B, the velocity time graph shows how the cyclist's velocity changes during part of the race. Right, you can see the velocity is increasing over time at first, so that means they are accelerating. Then you've got a steady speed, and then the velocity is coming down, so it's decelerating. During which part of the race is the resultant force on the cyclist zero? Right, well, it's either when they're not moving, or it's when they're moving at a steady speed. So moving at a steady speed, that's part B there. Because the forward force will be the same as the backward force, and that means that you're going at a steady speed. Part A here, you are accelerating because your speed's getting faster, your velocity's getting faster, so that must mean that there's more forward force than there is backward force. And for sections C and D, it's decelerating, so that would mean that there's more backward force than forward force. So the answer is B. That's when the forces are balanced, forwards and backwards are the same. Part 2, calculate the acceleration of the cyclist during the first 4 seconds. Okay, so acceleration equals the change in velocity, so V minus U. That's the final velocity, take away the initial velocity, divided by the amount of time that it took. So the first 4 seconds, so from 0 up to 4 seconds there. So if we go up to the graph, and then if we read off the graph there, so the speed, it started at 0 and it went up to 12. So the change is just 12, and the amount of time it took was 4. So 4 meters per second change divided by 4 seconds. And that comes out as 3 meters per second, or what we say is 3 meters per second squared. The diagram shows the horizontal forces acting on the cyclist in another part of the race. So 400 newtons to the left, 250 newtons to the right. They're examples of vectors, by the way, because there's the size and the direction. Calculate the resultant force on the cyclist and state its direction. So it's just like if it was tug of war. There's one team pulling to the left with 400 newtons and there's one team pulling to the right with 250 newtons. So the team pulling to the left's going to win. And how much are they going to win by? Well, 400 take away 200 is 150 newtons. So the force is 150 newtons and the direction is to the left. Size, direction. So that's a vector. Force is a vector. Question 2, electric charges. Complete this table for the 3 particles in an atom. The first row is being done for you. So particle name, proton. Protons, positive. It's got a massive 1. Neutron is neutral, and that's also got a massive 1. And the final particle is an electron. Its charge is -1, and they've already got the mass in for you. The mass is nearly 2,000 times smaller than the mass of the proton and neutron. B. A plastic rod is rubbed with a cloth. The plastic rod and the cloth become charged. Describe how you could show that the rod is charged. So the easiest thing is to put the rod next to some little pieces of paper and it'll pick it up. You could also say put the rod next to your hair and your hair will start to stand on end. Or you could say put the rod next to some flowing water and the water should attract over towards the rod. But I like the thing with the paper. Part 2. The plastic rod becomes positively charged. Complete the sentence by putting a cross in the box next to your answers. Compared with the rod, the cloth has, well, if the rod becomes positively charged, that's because it's lost electrons. That'll mean that the cloth has gained electrons, so that'll be negative. So an equal positive charge? Nope. An equal negative charge? Correct. So there's the rod, and there's the cloth. So the rod became positive. What that means is that electrons has jumped from the rod onto the cloth. So for every electron that the rod loses, the cloth gains. So if 1 electron goes over, the rod gets left +1 and the cloth would become -1. If another electron was to jump over, then that would be +2. And that would be -2. Part 2. Explain how friction between the cloth and the rod gives the rod a positive charge. So, friction causes electrons to transfer from the rod to the cloth. And that'll get you 2 marks. Number 3. Cars, power, work and energy. A car is travelling along a straight road. The driver has to brake suddenly. The thinking distance is 18 metres and the braking distance is 55. Calculate the stopping distance of the car. Total stopping distance equals thinking distance plus braking distance. So the thinking distance was 18 metres and the braking distance is 55 metres. So that comes out as 73 metres. So let's explain this a little bit. Now, just say a little old granny jumps out. You're driving a car, little old granny jumps out in front of the road. Your brain has to tell your foot to press the brakes. Now your car's travelling. So the amount of time that it takes for your brain to tell your foot to press the brakes, the distance that you've travelled during that reaction time is your thinking distance. Now, just because you've pressed the brakes doesn't mean the car's going to come to an immediate stop. The car has to mechanically come to a stop. So the distance that the car travels while the brakes are pressed, that's your braking distance. So your total stopping distance is your thinking distance added to the braking distance. State one factor that could increase the driver's reaction time. Right, well, what would make you take longer? If you're high on goofballs, so if you've taken drugs, or if you're drunk on alcohol, if you're distracted, so if you're on your mobile phone, any of those are good. Part 3. State one factor that could increase the braking distance of the car. Now, that's things like worn out tyres, worn out brakes, So the braking distance of the car, that's all to do with the car. The thinking distance is all to do with you, but the braking distance is all to do with the car. You could see bad weather, such as if there's water or ice on the road, that'll increase the braking distance as well because your car will skid. B, an airbag helps to reduce injuries in a collision. Complete the sentence by putting a cross in the box next to your answer. Airbags reduce injuries to drivers in a collision by, well, what they do, the amount of force that you have, so that's a big force will cause a big injury. It is to do with the change in momentum, so that's mass times by velocity. This triangle thing means change in, divided by the amount of time. So what an airbag does is it increases the amount of time taken for your head to stop. So instead of just nutting a hard steering wheel and instantly stopping, what you'll do is you'll nut the airbag, and then your head will come to a slower stop. So that'll increase the amount of time for the change of momentum to happen. And then mathematically, if this number on the bottom gets bigger, it makes this number on the top get smaller. And the change of momentum, by the way, will just be the same because you've got the same head, so that's the same mass, and it's the same velocity because you're in the car and the car's travelling at a certain velocity. So, airbags reduce injuries to drivers in a collision by decreasing the kinetic energy of a car. Nope, because kinetic energy is a half mv squared, so your mass is still the same, your velocity is still the same, so the kinetic energy is still the same. Increasing the time a resultant force acts on the driver. Correct. Let's have a look at these. Decreasing the driver's thinking time. No, just because you've got an airbag in does not decrease your thinking time. Doesn't make you react any faster. Increasing the rate of change of momentum of the driver. No, it doesn't affect your mass or your velocity, so that's not right. So B was correct. Question C. During braking, the car's brakes produce an average braking force of 14,500 newtons. Calculate the work done by the brakes over a braking distance of 5 meters. Calculate the work done. So work done equals force times by distance. Just lob the numbers in. So the force is 14,500 newtons. Multiply that by a distance of 5 meters, and that equals 73,000, and that's joules, or you could say Newton meters, but they want it in joules. And I would always show you working out, by the way. If it's good enough for me, it's good enough for you. D. After braking, the car accelerates. The car's engine does 800,000 joules of work in a time of 12.5 seconds. Calculate the power. Do you see what I'm doing each time? I'm underlining what it is it gives us and what it is that I need to work out. That's a good exam technique. I would do the same if I was you. So calculate the power. So power equals energy transferred or work done divided by the amount of time. So if you can do a lot of work in a small amount of time, that makes you very powerful. And power is measured in watts. 1 watt is the same as 1 joule per second. E. The car has a mass of 1,600 kilograms. Calculate the kinetic energy of the car when its velocity is that. So kinetic energy equals a half times by the mass times by the velocity squared. I've got a nice video on this on my channel, by the way, and that equals a half. I've got a nice video on power as well, by the way. A half times by the mass times by the velocity squared. Now remember to square the velocity first and then multiply it by the mass and then half it. So that equals 720,000 joules, if you're clever. Number 4, lamps in a circuit. A student experiments with filament lamps in a circuit. She starts with 1 lamp. Which of these circuits will let her measure the current in the circuit and the potential difference across the lamp? put a cross in the box. So ammeters have to be connected in series. They measure current. They have to be part of the circuit. So this A is wrong. B, ammeters part of the circuit. Yep. Now voltmeters need to be connected in parallel, which means across the component. Is that correct? Yes, it is. So it looks like it's B. Let's just have a look at C and D though. Well, the voltmeter is in series, so that's wrong. The ammeter is in series, so that would have been right, but you know, the whole thing's wrong then, isn't it? And this one, although it's got the voltmeter in parallel, it's got the ammeter in parallel as well, so that's wrong. B, the student finds that the current in the lamp is 0.8 amps. Calculate the amount of charge that passes through the lamp in 4 minutes. Right, well, if you're wanting to charge your mobile phone, Q, charge, that equals the current times by the time. So you need to plug your mobile phone into the mains so that it gets current, and you need to leave it plugged in for a certain amount of time. The more time that you leave it plugged in for, the more charge that your mobile phone battery gets, alright? Now this is the thing though, time has to be in seconds. So there's 60 seconds per minute, and there's 4 minutes, so that's 4 times by 60, that'll give you your total time. So you could say that's 0.8 times by 240 seconds, and that's 192 coulombs. Charge is measured in coulombs. Part 2. The student also finds that the potential difference across the lamp is 3 volts. Calculate the power of the lamp. Right, well, the power equals the current times by the voltage. PIV. So the current was 0.8 amps and the voltage is 3 volts. So that equals 2.4, and that is power, so that's watts. Part C. The student replaces the lamp in the circuit with a different one. The current in this lamp is 0.6 amps. When the potential difference, that's just the voltage, is 3 volts. State how the resistance of this lamp compares to the resistance of the first lamp. Right, well, simple as this. The current's got less, so that must mean that the resistance has got more. We use resistors to control the size of the current in a circuit. I like to think of a resistor as being like a dam. Okay, the bigger that you build the dam, the smaller it makes the water current. Well, the bigger the resistor, the smaller the electric current. And if they refer to the first lamp as the first lamp, then I'm going to refer to this new lamp as the second lamp. Now, if it was worth more marks and you had to back it up mathematically, here I'll show you some tricks. Right, we know that voltage equals current times by resistance. That's Ohm's law. So therefore, resistance equals the voltage over the current. So for the first lamp, the resistance will be 3 volts over 0.8 amps, which equals 3.75 ohms. And the second lamp, the resistance is, again, it was 3 volts. This time the current was only 0.6 amps, so that equals 5 ohms. So you can see the resistance of the second lamp is bigger than the resistance of the first lamp. But I told you that anyway without even proving it by calculation. But I'm just saying, if it was worth more than 1 mark, that's what I would be doing, okay? D. The student connects both lamps in parallel to the 3 volt battery as shown in the diagram. What is the size of the current in the battery? Right, Kirchhoff's law. The junctions are where the current can split. Now Kirchhoff's law says what goes into a junction must come out. So the current that goes in must come out, right? So what's happening is the current's coming along here, and some of it's splitting off this way. 0.6 amps is coming down here, and 0.8 amps is going down there. So if I call that I1, so current 1, I'll call that I2, current 2, and I'll call that I3, current 3. Kirchhoff's law says I1 equals I2 plus I3. So I2 is 0.6 amps and I3 is 0.8 amps. So that must mean that I1 was 1.4 amps. Boom! How do you like them apples? That's answer C. E. A filament lamp is one example of a component in a circuit. A light-dependent resistor can be another component in a circuit. A light is shone on a light-dependent resistor in a circuit. Explain how this changes the current in the circuit. Right, so you've just got to know that for an LDR, if the light shining on it is brighter, then the resistance decreases. Now, if you go on to do the higher level, or especially the triple, you'd have to know a little bit more about why that happens. So basically, as the light gets brighter, the resistance decreases. Now, it's seeing what happens to the current. So I told you before, if the resistance gets less, then the current gets more. That's like taking a dam and ripping your dam down. You're going to let more water flow, aren't you? More water current. Well, it's the same as electric current. So the current increases because the resistance has decreased. Question 5. One isotope of uranium is U-235. The nucleus can be represented as U-235-92. Complete the following sentence. And a nucleus of U-235 contains so many protons and so many neutrons. Right, well that bottom number there, the atomic number, that tells you how many protons there are, so that's easy peasy, that's just 92. And the number of neutrons, right, to get the number of neutrons you do the top number, take away the bottom number. That's 143. That top number there, by the way, is the total mass. Now, as we saw in one of the questions before, there's 3 subatomic particles in an atom. The only ones that got mass are the protons and the neutrons. So that mass number there comes from the number of protons and the number of neutrons. So if you take away the number of protons from the number of protons and neutrons, that just leaves you the number of neutrons. B. Uranium-235 decays by emitting an alpha particle. The table gives information about different types of radiation. Tick 2 lines that are correct for an alpha particle. So there's the symbol for an alpha particle. 4-2. It's got 2 protons and it's got a total mass of 4. So if it's got 2 protons, it must have 2 neutrons to make that number 4. It's an electron. Nope. Is electromagnetic radiation? Nope. Is 2 protons and 2 neutrons? Yes. Has a positive charge? Yes. Alright, because it's got 2 protons on it, and protons are positive. Got a negative charge? Nope. Has no charge? Nope. Part 2. Describe the ionizing and penetrating abilities of alpha particles. Right, ionizing. Like, because it's so big and heavy, it's like a big boxer. It's very ionizing. Remember, if something's ionizing, it means that it can hit an atom and it can knock an electron off it. So because alpha is very heavy, it can easily do that. So it is very ionizing. What about penetrating? Right, because it ionizes everything so much, it doesn't really travel very far. It runs out of energy. So it's not very penetrating. It travels about 1 or 2 centimeters in air. Now watch, here's a generalization, right? Do you know that there's 3 types of radiation? You got alpha, beta and gamma. Now they'll often ask you, what are the ionizing and penetrating powers? So alpha ionizing is the most, gamma is the least ionizing, and beta is the medium. So basically it goes like that, with alpha being the most. Now penetrating, alpha is the least, gamma is the most, and beta once again is medium powers. So this is getting more and more penetrating as you go down. So I hope that's helpful for you. Just a little generalisation. Question C. Uranium-235 can be used in nuclear fission reactions, but not in nuclear fusion reactions. Describe a nuclear fission reaction and a nuclear fusion reaction. Your answer should identify the differences between the two types of nuclear reaction. Right. So fission is about splitting nuclei of atoms. Don't just say splitting atoms. The examiners don't like it. You've got to say splitting the nuclei of atoms or nucleuses. Well, that doesn't really make sense. Split the nuclei of atoms by hitting the nucleus with a neutron. Smaller nuclei are formed. More neutrons are released, which can cause a chain reaction. Now I'm using this as an opportunity to recap fission generally. I would 1, 2, 3, 4, 5. I got 5 marks for that, but I'm probably only going to get 3 marks for it because I need to get my other 3 marks from describing the nuclear fusion. Watch, here's a picture to help you to understand it. There's the neutron. Now that goes and hits a big atom like uranium. Now that uranium is going to split into 2 smaller atoms. You don't need to know the names, but if you wanted to, that would be krypton and barium. Now this is the thing, right? 1, 2, 3 more little neutrons come out. By the way, energy gets released as well, right? Energy is released. Now these neutrons can go on to do further reactions by hitting into more uraniums, and that's your chain reaction. Fusion, well, if fission is about splitting large nuclei into smaller ones, fusion's the opposite. It's about taking smaller nuclei like hydrogens and smashing them together to make a bigger atom or bigger nucleus, helium. Energy is released. Now this part here might be just higher, but basically to get these to fuse together, it needs to be high temperature and high pressure. You've got to jam those atoms together, and that is to overcome forces of repulsion in the nucleus. Because if you think about it, the nucleus is positively charged, isn't it? So one positive charge is not going to want to go next to another positive charge. They're going to repel. So high temperature, high pressure, get those bad boys to come together, and when they hit, they'll join together rather than just bounce off. So that's a whopper. You don't have to put all of that detail, but I'm just, you know, if there is a question to do with fission and it's worth 6, well, you'll get 6 just for that alone. Or if there's a question to do with fusion, that's worth at least 4 marks there. Uses and dangers of radioactivity. Number 6. Medical supplies such as the bandage shown in the photograph have to be sterilised before they are sold. There are 2 ways of sterilising medical supplies. They can be heated to a high temperature in an oven, or they can be irradiated using a radioactive isotope. Suggest one advantage of using radiation rather than high temperatures to sterilise medical supplies. It's a bandage, which is cloth. If you shove it in the oven, it's going to damage, isn't it? You're going to bake it, you're going to burn it. Part 2. Cobalt-60 is a radioactive isotope used to sterilise medical supplies. Cobalt-60 has a half-life of 5 years. Calculate how long it takes the activity of a sample of cobalt-60 to fall to 1/4, so 25% of its original value. Right, well, if we say the original value is 100%, a half-life later we'll have 50%. Another half-life later we will have 25%. So remember, the half-life is the amount of time that it takes for either the activity to half or for the number of radioactive nuclei to decay by half. So there we go. Now the half-life's 5 years, so that's going to be 5 years there, because that's one half-life, and then another half-life, that's another 5 years. So 5 years plus 5 years equals 10 years. B. This is part of an article in a newspaper. A truck carrying a large quantity of cobalt-60 was stolen by thieves. They get everywhere, don't they? The next day, a farmer found the stolen truck in his field. The cobalt-60 was on the ground, with its protective shielding removed. Oof, naughty. The cobalt-60 was later recovered by radiation specialists. State one way that the cobalt-60 could be a danger to the health of the farmer. Right, it's radioactive, it's always the same pattern. It could damage his cells and cause cancer. Or you could say it could give him radiation poisoning, or it could give him radiation burns. Don't just say it could kill him, right? The examiners don't like that. Part 2. Suggest 2 precautions the radiation specialists should take when they recover the stolen cobalt. Well, the first thing to do is put some shielding back on it. Now, other ways to minimise your exposure would be to stay away from it, but that's not going to happen because they've got to go in and pick it up. But you could say get them to pick it up using tongs. Put some protective gloves on as well. Wear some kind of lead-lined clothing because lead absorbs alpha, beta and gamma. But I'm happy with the 2 answers that I've put down there. You could have also said keep the public away and maybe dig up the soil that it's been lying on, pop that into bags and take that away just in case it's irradiated as well. Part C. The table shows information about cobalt-60 and 2 other radioactive isotopes. Right, what's going on here? So there's 3 different isotopes, tells you the type of radiation that gets emitted, so that one gives off gamma, that one gives off alpha, that one gives off gamma. Half-life, that one's 5 years, 11 days and 15 hours. Medical supplies in cardboard boxes are sterilised using radiation. Use the information in the table to explain why cobalt-60 is better than the other 2 isotopes for this purpose. Now, when you sterilise something, you're basically using the energy from the radiation to kill off any microorganisms and little germs and things like that. Which one's got the most energy out of gamma and alpha? Well, gamma. So you're either looking for cobalt-60 or the sodium-24, but check this one out. That's got a half-life of 5 years, which is decent, so that means you don't need to replace it for a while. That one's only got a half-life of 15 hours, which means that every 15 hours it just decreases its strength by a half. That's going to run out. You're going to have to replace that all the time. So your answers are going to be based around that information. Sorry about me writing, it's terrible. Right, so I've put a couple of things about the cobalt, a couple of things about the sodium and a couple of things about the radium. I would encourage you to quote the values from the table that it's gave you, but I would also encourage you to interpret that information. Don't just say, cobalt gives off gamma, which has got a half-life of 5 years, Alright, thanks very much for being able to read the table, but you haven't told us what that actually means in your understanding. Alright. Boom, and another one bites the dust. Looks like I finished it. Nice. Well, I hope that was useful. I'll be putting more out there, higher ones and some triple ones as well. So stay tuned for more. Thanks very much for all your support from each channel. Bye for now.